So that's the notation, standard IEEE notation, same as we used last quarter. And so now, the first topic is windows. So spectral content varies over time, and the key reason we need windows is that the human ear does a Fourier transform, but it does it over a short period of time. And I use the term Fourier transform loosely. It's a kind of Fourier transform. It's a spectrum analysis that is over, it's actually a duration that varies with frequency. It's nearly constant Q. And remember from last quarter that constant Q means the same number of cycles at all frequency. And so the ear is essentially approximating a constant Q Fourier transform. So its Fourier transform length is the same number of cycles at all frequencies, more or less. Let's say approximately, especially above, let's say 500 hertz. At low frequencies, it's more linear. So we want to follow that Q. That allows you to hear a different spectra at different time. And so you're not hearing a Fourier transform, you're hearing a short time Fourier transform. You're hearing a signal with spectral components estimated over a finite duration. And so another reason this comes up when we're doing FFT convolution is that we don't want to read the whole sound file into memory and take a giant Fourier transform and then multiply that by the frequency response in inverse transform. Well, because we may not have enough memory for that, although that's getting less and less true. More and more sound files will fit in memory these days. But even then, it's still not optimal. There's an optimal block size that's not the whole signal if you want to minimize computational complexity. So what we do is we break up our signal into blocks, and we FFT each block and then multiply it by a frequency response and inverse FFT that block. And we just keep going until we get to the end of the file. So these are indicating blocks. So we'll be doing that. So we're going to need FFT windows. And the simplest case is the rectangular window, and that's what I've drawn here, where you just chop out a chunk of the signal. So there's a signal running through here, and I'm just taking out, I'm just chopping out a segment, and you can think of that windowed segment as a rectangular window having been multiplied by the signal. So first thing we'll look at is the rectangular window, and then we'll look at better windows. And better means it has better properties. So the problem with the rectangular window is that its frequency behavior is not ideal. And we'll be using windows for different things, and so we want better windows for different applications. All right, so that's it. Now it's time to look at some windows.